Cool. Thanks. Hi, everyone. My name is Catalin. I'm part of IP engineering at OneWeb. So, like the slide says, we'll discuss multicast routing, which is a fun topic in any network. So, about OneWeb, for those that are not familiar with us, we are a telecommunication company. We aim to provide connectivity via our constellation of satellites. We partner with various people and organization, governments, telecommunication company, and we are trying to connect as many people as possible.
Can you just keep a bit closer to the mic?
Oh, sure. Yeah, sorry. Okay. So our satellite, our constellation, it's a LEO satellite, very close to Earth. We provide low latency communication and right. It's on that slide. We have many terminals and we connect a lot of end customers, being airplane, aviation, sea, or fixed communication. In terms of network, we have gateways, which are sites with big antennas that we discuss with the satellite, and then we have POPs, where the logic of IP providing connectivity, that's in the POPs. We interconnect with, as I mentioned, various customers. We provide internet access for demo, and most of our business is our service is business-to-business model. The way the network is, or the way the network was when this slide was taken, we covered the whole globe. We need global coverage. We have point of presence and sites in most of the world, as you can see here. Yeah, this is a slide that our marketing said, we are done with you, and from now on you have my diagrams, not the fancy graphic that the company provided. So in terms of network, it's a standard IP network, nothing out of ordinary here. We have two layers. We have the access layer, which is where the satellite communicates with the ground networks. Then we have the MPLS network, and it's like any other MPLS network. We have edge routers, we have core routers, and in the context of multicast, we have our RPs. On the access network, we run the CE. It's inside the VRF on our routers. Then on the edge and core, we run ISIS, we run LDP and segment routing, with segment routing being the preferred protocol. MPBGP and PIM, of course. In terms of multicasting, and why do we need it and how do we use it? There are many use cases in our network, and most important, right, it's the satellite communication, handovers between satellites, some telemetry systems, and a bunch of other traffic that requires multicast. So for our solution to work, multicast needs to be enabled and needs to be working as expected. We have a lot of sources and groups in the network, so I think we have around 150 or more sources per site. We have lots of sites, and for today's discussion is just right, when a satellite passes through a gateway, he needs to tell the other gateway that he will be there in a couple of minutes, or to be precise, a couple of seconds. So as I mentioned, for us, it's a lot of sources in one site. This is a snapshot of our monitoring tool. Every line there, it's a group and a source pair. We are a busy network in terms of multicast routing, about 9,000 or so active routes, and about 7,600 source active. The difference is some other BGP routes that we have there. Okay, so our multicast, as I mentioned, it was part of the global routing table, and the whole point of mVPN is to migrate that traffic from the global routing table to VRF or a routing instance. And why we needed to do that? There were a couple of challenges. We need sub-second convergence in the network. We are trying to get away from the state on the P nodes. And of course, we wanted the P nodes to be BGP free for various reasons. What we ended up with after looking at the options, we ended up with mVPN. And for the transport, we use MLDP. The reason we use MLDP is it was already active in the network. We had for unicast traffic, and then once we migrated to segment routing, LDP was there. It was easy to flip a switch and enable the multicast extensions. We can achieve sub-second with MLDP fast reroute, which I'm going to go into a bit more detail, but it's ECMP or LFA dependent. So that sub-second is in specific conditions, and we'll talk about the specific conditions. What we achieved with the mVPN is instead of having the state in PIM, then we migrated everything to fancy new family in BGP and more BGP routes, I guess. Having the multicast being MPLS switch, that means we can finally take the BGP out of our core nodes. And yeah, maybe deploy some nodes that are not that powerful. I don't know, anyone using multicast or mVPN in their networks? One hand, no? Got one. Okay. So maybe the refresher will help. So the mVPN, it's a new family in BGP. It has multiple type of routes. So if you're familiar with EVPN, maybe you can relate. There are a couple of type of routes. And the most important ones, right, the type 1 is where the devices discover each other. Then type 5 and type 7 are routes that instead of PIM joins and reports and IGMP, those get translated into BGP routes, and we'll go into a bit more detail. So the refresher, in terms of transporting multicast, you have many options to transport multicast in mVPN. We chose the LDP, MLDP, and this is just the way that it works. It's a BGP advertisement from every P in the network to all other Ps discovering each other. A message goes from each one to the route reflector, and then it gets propagated into the network. So that way we can build a tree. So on the control plane, it goes from the receiver towards the root of the tree, which is the source, and it goes hop by hop, and then every router allocates a label, and there is a label merge at some point, if there is a case, and then the traffic starts flowing from the source towards the receiver using those labels. So in terms of migration, it wasn't an easy one to do because, as I mentioned, we are a global network. We have live customers, and we are very latency sensitive. So we had to create the migration plan. So what we ended up with is we created a new VPRN into our network, a new VRF or new routing instance with nothing in it. We deploy it everywhere. And then we created the RPs inside those VPRN. And then we had two central sites, one in US and one in Europe, where we linked the global routing table with this VPRN. So we did that with a physical loop. Like any other engineers in the world, I think everybody had a physical loop somewhere in the network. We did it as well, even if it's not next gen, but it worked. And then we, as I mentioned, link the GRT RPs with the VRF RPs using MSDP. And then we move to all sites and migrated from the global routing table in this VPRN. We are a very delay sensitive network, in a sense that if we are bypassing some threshold, the system does not function. So sometimes when we did the migration, we had to take 3 sites at a time, 4 sites at a time, and do the migration in that way. So how does it look on a diagram? In terms of messages, this is a sender in the global routing table and the receiver in the new VRF that we deployed. And it follows that leak site model. So you get a join from the customer, it goes to RP, and then via MSDP between the sites, and then it gets BGP propagated along the way. Then if you turn it around and you have the sender in the VRF and the receiver in the global routing table, similar messages are exchanged, but right, you have a register towards the RP in the VRF, then source active via MSDP to the global routing table, and then traffic starts flowing. So, of course, when we finish the project and all the sites are migrated, then the complexity is not that high anymore, because everything is restricted to the VPRN, to the VRF itself. We understand the messages, same type of messages. The only minus is that we don't use this leak site anymore. So MSDP is not in place anymore, and everything starts working through the VRF itself. So it took a while for us to migrate, and you can see in this timeline we started, and not that much traffic happened. This is the part where the project started, and we had to make sure the control plane works as expected. So there is not much traffic on our leak sites. And then we slowly tested, and some bumps there. And then we, for each of our leak sites, we run the load testing, making sure that the solution is scalable and we can send as much traffic as we want. And then slowly we started migrating the traffic, and the trend is there. So in terms of migration, I think it's been a success for us. We learned lots of things. And the ones that I really want to emphasize is the BGP convergence. That's the part where we were caught off a bit off guard. And if you do any type of migration involving BGP, make sure you know the convergence and make sure you measure the convergence, and you can refer back to it. Just in case other protocols are failing, you make sure that BGP is stable and you know exactly the convergence time. We had to put dedicated route reflectors. You might say, yeah, well, usually you do that. But again, we didn't want to increase the complexity of the solution by adding new devices. We only did that when we found out that our existing route reflectors would not scale to the numbers we wanted. I mentioned LFA for sub-second convergence, and when I say LFA, I'm not referring to TI LFA or remote LFA, pure LFA. Well, software defects, lots of them, of course. With this type of migration, it's bound to happen. Everything has a bug or two. The ones that we encounter are listed there, right? Fragmented PIM join and prunes are discarded. MSDP fails to send a source active if the packet is above 1500. High CPU, platform scaling, that's probably not a bug, but something that we only found out during the migration and in some race conditions. What we found during the migration and in this type of project is not being afraid to look at some old design decisions and change those if they don't really work anymore. It's a completely different approach to having the multicast in the global routing table versus having the multicast in a dedicated routing instance. So we had to go and change the BFD on some multicast routes. We had to make sure BGP backup path is there for our sub-second convergence. We had to enable BFD on LDP and not only on ISIS core interfaces. IGP timers, and most important, we had to redo our end-to-end testing a couple of times. Every change in the design requires an end-to-end testing, making sure you are not introducing new bugs or new problems. In terms of BGP, like I mentioned, it's important to understand your convergence in the network, and for us, because mVPN sits on top of BGP, if we want sub-second convergence for multicast, we need a control plane to converge sooner than that, of course. So it's been an exercise for us to understand the convergence, and this is how it looks like in OneWeb Network. Our route reflectors are split between 3 regions, America, EMEA, and APAC. We have a full mesh of session between the route reflectors, and then each client peers with their specific region. So our convergence is less than 200 milliseconds in the worst case scenario. So on the left side, you see we have a site in Costa Rica. We flap a route there, and then we measure via our monitoring how much it takes, how much time it takes for that update to be reflected in various clients. So Australia, Italy, and US. LFA convergence, it's important for MLDP to make sure there is a backup path in the network already programmed. MLDP requires LFA or ECMP. So in terms of our network, we have full coverage for about 26%, and then you see the numbers there. But what's not shown, and this graph is misleading a bit, is because not all sites talk to all sites. So an example will be Greenland. From us, Greenland, in terms of the system to function, it needs to talk with London, Toronto, Calgary, and Ashburn, the sites that Nuke talks with. It doesn't talk with Palermo, for example. So having 100% coverage to Palermo nodes from Greenland does not help. It just paints a good picture, but it's not something that will be used in real life anyway. So it's always a balance between making sure you have enough capacity, you have decent latency, and LFA coverage. There is no way for us to provide 100% coverage to everything. So when we design first of all for low latency links, and second for high convergence. There's always room to improve, and hopefully we get to a stage where all our sites are 100% full coverage in terms of LFA. After we did the migration, of course, we are done with this project. We are looking at ways to improve, and because of the findings in the migration, there are a couple of things that we want to do going forward. First of all, we really would like to move away from MLDP, and we are looking at alternatives. Beer is one of them. Segment routing, because we have segment routing for unicast, we have segment routing for traffic engineering, so it makes sense for us to look at SR point-to-multipoint policies. In the meantime, we are looking for our vendors to support remote LFA or TLFA for MLDP, which, to be honest, it's a long way. Some of the drafts are there, but I don't think the implementation will be there. So most likely we are looking at SR point-to-point policies. We are talking with our partners to maybe redesign the application if we can get away from multicast, or do we still need to keep it? at scale, we are looking at ways to decrease the source active to a manageable amount, and then we can deploy SPMSI, which is not everybody talks with everybody, just a specific size to all of them. So that's OneWeb project, and OneWeb, just a peek of what we are doing in IP engineering for OneWeb. And I think I'm in time, yes, for questions.
Hi, Greg Choules, ISC. Thank you. Very interesting talk. Do you have to keep PIM and RPs, or can you move to SSM?
We need to keep RPs. We run ASM, we can't move to SSM.
Okay, thank you.
And just to put some context, is because the application is designed like that, like always.
That's everything.
Brilliant.
Catalin, thank you very much. Thank you.